To hear the shape of a drum is to infer information about the shape of the drumhead from the sound it makes, i.e., from the list of overtones. Via the use of mathematical theory, can one hear the shape of a drum? Was the title of an article by Mark Kac in the American Mathematical Monthly in 1966. But the phrasing of the title is due to Lipman Bers. These questions can be traced back all the way to Hermann Weyl. For the 1966 paper that made the question famous, Kac was given the Lester R. Ford Award in 1967 and the Chauvenet Prize in 1968. The frequencies at which a drumhead can vibrate depends on its shape. The Helmholtz equation calculates the frequencies if the shape is known. These frequencies are the eigenvalues of the Laplacian in the space. A central question is whether the shape can be predicted if the frequencies are known. No other shape than a square vibrates at the same frequencies as a square. Kac did not know whether it was possible for two different shapes to yield the same set of frequencies. Formal statement. More formally, the drum is conceived as an elastic membrane whose boundary is clamped. It is represented as a domain D in the plane. Denote by lambda n the Dirichlet eigenvalues for D. That is, the eigenvalues of the Dirichlet problem for the Laplacian. Opening curly bracket. Delta U plus lambda U equals 0. U pipe D equals 0. Display style begin cases delta U plus lambda U equals 0. U underscore partial D equals 0 end cases. Two domains are said to be isospectral or homophonic if they have the same eigenvalues. The term homophonic is justified because the Dirichlet eigenvalues are precisely the fundamental tones that the drum is capable of producing. They appear naturally as Fourier coefficients in the solution wave equation with clamped boundary. Therefore the question may be reformulated as, what can be inferred on D if one knows only the values of lambda n? Or, more specifically, are there two distinct domains that are isospectral? Related problems can be formulated for the Dirichlet problem for the Laplacian on domains in higher dimensions or on Riemannian manifolds, as well as for other elliptic differential operators such as the Cauchy-Riemann operator or Dirac operator. Other boundary conditions besides the Dirichlet condition, such as the Newman boundary condition, can be imposed. See spectral geometry and isospectral as related articles. The answer. Almost immediately, John Milnor observed that a theorem due to Ernst Witt implied the existence of a pair of 16-dimensional tori that have the same eigenvalues but different shapes. However, the problem in 2 dimensions remained open until 1992, when Gordon, Webb, and Wolpert constructed, based on the Sunada method, a pair of regions in the plane that have different shapes but identical eigenvalues. The regions are concave polygons. The proof that both regions have the same eigenvalues is rather elementary and uses the symmetries of the Laplacian. This idea has been generalized by Buser et al., who constructed numerous similar examples. So, the answer to Kac's question is, for many shapes, one cannot hear the shape of the drum completely. However, some information can be inferred. On the other hand, Steve Zeldich proved that the answer to Kac's question is positive if one imposes restrictions to certain convex planar regions with analytic boundary. It is not known whether two non-convex analytic domains can have the same eigenvalues. It is known that the set of domains isospectral with a given one is compact in the C-infinity topology. Moreover, the sphere, for instance, is spectrally rigid, by Cheng's eigenvalue comparison theorem. It is also known, by a result of Osgood, Phillips, and Sarnak, that the moduli space of Riemann surfaces of a given genus does not admit a continuous isospectral flow through any point, and is compact in the Frechet-Schwarz topology. Weyl's formula. Weyl's formula states that one can infer the area V of the drum by counting how rapidly the lambda n grow. We define n, r, to be the number of eigenvalues smaller than r, and we get V equals 2 pi d lim r infinity n r r d slash 2. Display style V equals 2 pi caret d lim underscore r 2 inf d frac n r r caret d 2. Closing curly bracket, where d is the dimension. Weyl also conjectured that the next term in the approximation below would give the perimeter of D. In other words, if A denotes the length of the perimeter, or the surface area in higher dimension, then one should have n r equals 2 pi minus d omega d v r d slash 2 plus 1 4 2 pi minus d plus 1 omega d minus 1 a r d minus 1 slash 2 plus o r d minus 1 slash 2. Display style n r equals 2 pi caret d omega underscore d vr caret d 2 plus frac 1 4 2 pi caret d plus 1 omega underscore d 1 r caret d 1 2 plus o r caret d 1 2 backslash closing curly bracket, where omega d display style omega underscore d is the volume of a d-dimensional unit ball. For smooth boundary, this was proved by Victor Ivory in 1980. The manifold is also not allowed to have a two-parameter family of periodic geodesics such as a sphere would have. The Weyl-Berry conjecture. For non-smooth boundaries, Michael Berry conjectured in 1979 that the correction should be of the order of r d slash 2 display style r caret d 2 closing curly bracket, where d is the Hausdorff dimension of the boundary. This was disproved by J. Brossard and R. A. Carmona, who then suggested one should replace the Hausdorff dimension with the upper box dimension in the plane. This was proved if the boundary has dimension 1. 1993, but mostly disproved for higher dimensions. 1996. Both results are by Lapidus and Pomerantz. See also vibrations of a circular drum. Gassman triple. Isospectral. Spectral geometry. An extension to iterated function system fractals. Notes. Abacoff, William. January 1995. Remembering Lipman Bers. PDF. Notices of the AMS. 42. 1. 8–18. Brossard, Jean. Carmona, René. 1986. Can one hear the dimension of a fractal? Quote. Com. Math. Phys. 104. 1. 103–122. Bibcode. 1986 CMAPH. 104. 103b. DOI. 10.1007, BF01210795. Buser, Peter. Conway, John. Doyle, Peter. Semler, Klaus Dieter. 1994. Some planar isospectral domains. International Mathematics Research Notices. 9. 391 ff. Chapman, S. J. 1995. Drums that sound the same. American Mathematical Monthly. February. 124–138. Giraud, Olivier. Thas. Cohen. 2010. Hearing shapes of drums, mathematical and physical aspects of isospectrality. Reviews of Modern Physics. 82. 3. 2213-2255. Arxiv. 1101.1239. Bibcode. 2010 RVMP. 82.2213G. DOI. 10.1103. RevModFees. 82.2213. Gordon. Carolan. Webb. David. You Can't Hear the Shape of a Drum. American Scientist. 84. January to February. 46 to 55. Gordon. C. Webb. D. Wolpert. S. 1992. Isospectral plane domains and surfaces via Riemannian orbifolds. Inventions Mathematicae. 110. 1. 1 to 22. Bibcode. 1992 Inmate. 110. 1G. DOI. 10.1007, BF01231320. Ivory. V. Yar. 1980. The second term of the spectral asymptotics for a Laplace-Beltrami operator on manifolds with boundary. Functional. Anal. I. Prilogen. 14. 2. 25 to 34. In Russian. Kac. Mark. April 1966. Can One Hear the Shape of a Drum? Quote. PDF. American Mathematical Monthly. 73. 4. Part 2. 1 to 23. DOI. 10.2307 2,313,748. JSTOR 2,313,748. Lapidus. Michel L. 1991. Can One Hear the Shape of a Fractal Drum? Partial resolution of the Weyl-Berry conjecture. Geometric Analysis and Computer Graphics. Berkeley. CA. 1988. Math. Sci. Res. Inst. PUBL. New York. Springer. 17. 119 to 126. Lapidus. Michel L. 1993. Vibrations of Fractal Drums. The Riemann Hypothesis. Waves in Fractal Media. And the Weyl-Berry conjecture. In B. D. Sleeman and R. J. Jarvis. Ordinary and Partial Differential Equations. Volume 4. Proc. 12th Internet. CONF. Dundee. Scotland. UK. June 1992. Pittman Research Notes in Math. Series. 289. London. Longman and Technical. pp. 126 to 209 CS1 maint. Uses editors parameter. Link. Lapidus. M. L. Van Frankenhuizen. M. 2000. Fractal Geometry and Number Theory. Complex Dimensions of Fractal Strings and Zeros of Zeta Functions. Boston. Birkhauser. Revised and enlarged, second edition to appear in 2005. Lapidus. Michel L. Pomerantz. Carl. 1993. The Riemann zeta function and the one-dimensional Weyl-Berry conjecture for fractal drums. Proc. London Math. Soc. 3. 66. 1. 41 to 69. DOI. 10.1112 PLMS per second 3 to 66.1.41. Lapidus. Michel L. Pomerantz. Carl. 1996. Counter-examples to the modified Weyl-Berry conjecture on fractal drums. Math. Proc. Cambridge Philos. Soc. 119. 1. 167 to 178. Bibcode. 1996 MPCPS. 119. 167L. DOI. 10.1017, SO3050041000740553. Milner. John. 1964. Eigenvalues of the Laplace operator on certain manifolds. Proceedings of the National Academy of Sciences of the United States of America. 51. 542 FF. Bibcode 1964 PNAS. 51. 542 M. DOI 10.1073 PNAS. 51.4.542. PMC 300113. PMID 16,591,156. Sunada, T. 1985. Riemannian coverings and isospectral manifolds. Ann. Of Math. 2. 121. 1. 169 to 186. DOI 10.2307 1,971,195. JSTOR 1,971,195. Zeldich, S. 2000. Spectral determination of analytic biaxisymmetric plane domains. Geometric and functional analysis. 10. 3. 628 to 677. DOI 10.1007 PL00001633. Isospectral drums by Toby Driscoll at the University of Delaware. Some planar isospectral domains by Peter Buser, John Horton Conway, Peter Doyle, in Klaus Dieter Semler. Drums That Sound Alike by Ivers Peterson at the Mathematical Association of America website. Weisstein, Eric W. Isospectral Manifolds. MathWorld. Ben-Gurion, Raphael D. 2001. Dirichlet Eigenvalue. In Hazewinkel. Muschiel. Encyclopedia of Mathematics. Springer. ISBN 978155608-010-4.